Hello everyone. The title is Quantum Security and Implementation Evaluation of Non-Adaptive Group Testing Aggregate Message Authentication course. And the authors are Hiroaki Anada and Daiki Kamibayashi with University of Nagasaki. Message authentication code works for integrity and authenticity. On input a message and a symmetric key, the MAC algorithm generates a tag, and the sender sends the pair of the message and the tag. Using the tag, the receiver is able to detect whether the pair was forged or not. Aggregate MAC, proposed by Katz and Lindell, works as a bandwidth-reducing mechanism. It aggregates tags by, for example, bitwise exclusive OR of all the tags. However, AMAC is not capable of identifying forged messages, though the detection is possible. Non-adaptive group testing AMAC, NAGT AMAC, proposed by Hirose and Shikata, attains the functionalities of integrity, authenticity, bandwidth reducing, and forgery identification. It uses a group testing matrix in combinatorics. According to the design of the matrix, the receiver executes tests, and the receiver can identify the forged messages by using the test results. On the other hand, Sato and Shikata studied security of AMAC and the threat of computational power of quantum computers. It was proved that the Katz-Lindell construction of AMAC is existentially unforgeable against quantum chosen message attacks if the component MAC has the same property. Our contribution in this study is we defined quantum security of NAGT AMAC. The first is identifiability, and the second is unforgeability, where the both are under quantum consideration. We evaluated efficiency of NAGT AMAC by software implementation. Here is a scheme of NAGT AMAC due to Hirose and Shikata. It is a generic construction using AMAC as black box components. In a nutshell, the construction is under the principle that aggregate in each row according to the design of the group testing matrix. Then we define quantum security by introducing the notion of quantum tagging query to the security definitions of identifiability and existential unforgeability. Here, quantum tagging query means that an adversary can issue tagging query with quantum superposed messages. Our first result is that if any adversary forges at most D messages among N, then the scheme has identifiability. And if AMAC has existential unforgeability against quantum chosen message attacks, then so is NAGT AMAC. Here we note that there is no need of quantum consideration in reducing quantum security. Next, we explain our implementation evaluation. We did a proof of concept implementation of an NAGT AMAC scheme with Python 3 language. Note here that a component MAC is hashMAC, HMAC. It generates a tag by hashing. Then, using HMAC, AMAC and NAGT AMAC are constructed. Our second result is that In the case that D is equal to 1, NAGT AMAC is only 30% slower than AMAC. But here we note that Python 3 language is an interpreter. In the case that n is equal to 1000, when D is 10, which is 1% of the number n, the total execution time is less than 0.5 seconds. This result is due to our software improvement of treating the group testing matrix by holding only the non-zero entries. As a conclusion, NAGT AMAC is efficient and it achieves quantum security. However, we must say that we have not evaluated the rate of the needed D-disjunctiveness, which leads to identifiability of forged messages. It will be our future work. Thank you.